Hello everyone, my name is Sava and I want to tell you about the shortest walk problem in graphs of convex sets. It is a mathematical problem that is amenable to effective computational solutions and at the same time is able to simultaneously capture a wide variety of interesting robotics problems that involve a mix of discrete and continuous decision making. Let's get to it. Let's start with a little bit of context. If we had a directed weighted graph with non-negative edge lengths and we're given a pair of source and target vertices, then a path through a graph is a sequence of distinct vertices connected by the edges, and a walk through a graph is a sequence of not necessarily distinct vertices connected by edges. We could then seek a shortest path for a walk through a graph, and that's the one that minimizes cumulative edge lengths. And it's easy to show that for a graph with non-negative edge weights, the shortest walk is a path. Indeed, suppose shortest walk was not a path, then it would have a non-negative cycle, then we could just remove that cycle and get a path whose cost is no higher than the original. Right? So in a classical graph, the shortest walk problem reduces to the shortest path problem. Let's now take a look at graphs of convex sets. It's a structure that generalizes the classical graphs by assigning a convex set to every vertex. Right? So now anytime you visit a vertex, you must also select a continuous point inside of that set. When you traverse an edge, you must select two continuous endpoints, right, that must in turn belong to this edge constraint set, and then you must pay a convex edge cost that is a function of these endpoints. It's a graph of convex sets. Paths and walks of graphs of convex sets are defined kind of intuitively, where a path is a sequence of distinct vertices together with the corresponding continuous points, and a walk is a sequence of not necessarily distinct vertices. So here I am assuming that we have self-edges, and whenever you revisit the same vertex, you can select a different continuous point. Now, what's interesting is that in this particular example, I'm using for the edge cost 1 plus the squared distance between the points, just to say that we want on one hand minimize the number of total steps, and on the other, we don't want the steps to be too big. And the cost of the shortest path here is 21, while the cost of the shortest walk is just 14. And this is achieved by taking smaller steps and thus not having to pay that large square penalty. So, unlike the classical case, the shortest walk in a graph of convex sets need not be a path, right? So it's a distinct problem in its own right. Now, the shortest paths in graphs of convex sets have lots of successful robotics applications pictured in these slides here. And in many of these cases, the convex sets more or less represent operational modes or contact modes. So the constraint that you have to visit each vertex or contact mode once can be limiting, right? Because the optimal solution might want to visit the same mode multiple times. Now, you could potentially duplicate these contact modes, just kind of repeat the vertices, but that's computationally inefficient. So the shortest walks come to the rescue. Next, I'm going to go into some specific representative examples where the shortest walk formulation offers a more natural transcription than the shortest path formulation. And these will serve as motivating examples for us to then solve the shortest walk problem in the first place. And I want to emphasize that our solution will be general enough to capture all of these applications. Let's get to it. My first example is going to be in optimal control of hybrid systems, or specifically piecewise affine control systems. These are systems described by a state space and a control space, where the state space is partitioned into a discrete set of control modes. Right? And for every control mode, the system will evolve according to mode-specific affine dynamics and will incur a mode-specific cost whenever executing an action in a state in that mode. Right? Piecewise affine control systems capture a wide variety of systems, especially those that involve contact, such as walking robots. But for the sake of an example, I'll use a super simple system, which is an actuated pendulum with a soft wall. Right? So there are just two contact modes here. There's no contact and when we are in contact. And then to construct a graph of convex sets, we're going to add a GCS vertex for every contact mode. Here's just these two. We're going to add appropriate edges if we can transition between the contact modes. And then we're going to add edge constraints, which are the affine dynamics and the appropriate edge costs. Right, so then a walk through this GCS is equivalent to a piecewise affine trajectory, so piecewise affine optimal control can be cast as the shortest walk in a GCS. My next example is going to be in skill composition. I'm going to use this simple pick and place example. Given a set of skills, such as move the arm, move the object, or flip the object, Our goal is going to be to compose these skills in series to achieve some goal condition. Here is just to put all the objects inside the target region. These kind of problems are more commonly known as task and motion planning. Right? So let's slightly more formally define what a skill is. Given a state space, a skill transitions this system from one part of the state space to another. Right? It is thus defined by a set of tuples, x prime, of these feasible transitions. These transitions can be achieved by some low-level policy whose dynamics we want to abstract away intentionally. Right? And in this simple example for flipping, I can map these horizontal object positions into a set of vertical object positions. And that would be my set of feasible transitions. It will then, each skill will also have a cost of executing this transition using this skill. And again, in this example of flipping an object, this might be a distance traveled by the arm. So now let's construct a graph of convex sets. We'll add a GCS vertex for every skill. Right? So the vertex set will be the set of feasible transitions, and visiting a vertex thus corresponds to executing a particular skill, and will also incur a skill cost. Right? And then we'll connect two vertices, or two skills, with an edge if after applying skill 1 you end up in a state where you can apply skill 2. Right, so then a walk through this graph of convex set is equivalent to a chain of skills, and thus shortest walk in this GCS is searching for an optimal skill chain. My final example is going to be in collision-free motion planning, where the shortest walk formulation allows us to spend arbitrary number of steps in each region, but in the interest of time I'm going to omit this example and refer you to the paper for the transcription. To ground kind of all of these ideas and applications, here is a peek into the results section from the paper, where we are applying these ideas to footstep planning, pick and place, and collision-free motion planning in a warehouse for warehouse-like robots. Okay, great. So how are we actually going to solve the shortest walk problem in GCS? This problem is NP hard, so we don't expect any efficient solution algorithms, so we'll focus on approximate or practical ones. One approach is to reduce this problem to the shortest paths in GCS, right? Because a walk in this graph is equivalent to a path in this layered graph that is attained by duplicating the vertices. But as we'll show later, this is extremely inefficient. Our proposed approach is very similar in flavor to the work that I presented at WAFR 2 years ago. Here's the citation, where we're going to first compute the cost to go lower bounds across the graph, and then we'll use incremental search to extract the walk one step at a time. Let's get to it. Let's talk about cost to go synthesis. First, we'll make an interesting observation, which is that the principle of optimality holds for this problem. Right? So every subwalk of a shortest walk is itself a shortest walk. This is kind of really intuitive to see, right? If this subwalk wasn't optimal, then we could just swap it. We can just swap it out for the optimal walk, and we'll get a walk of lower cost, right? So the principle of optimality holds for this problem. Next, we're going to quickly define the cost to go function. For every vertex, we're going to define a function ju star over that vertex, where the value of that function at every point is just the cost of the shortest walk from that point to some fixed terminal point. Right, so now we are ready to derive the Bellman equation for this problem. Let's examine the shortest walk from some point xu in the graph, and let xv be the next point in the optimal walk from xu. Right, so then by the principle of optimality, j star of the cost to go at xu is the cost of this one-step transition plus the subsequent cost to go. Right, and since this transition from xu to xv is optimal, then it must minimize this one-step sum over all other possible transitions. Right, and that's the Bellman equation, right? The cost to go at xu is the minimizer over one-step cost to goes over all feasible transition, over all edges and all feasible continuous point pairs. Right, so that's the Bellman equation, and if we find functions, j, for every vertex that satisfy this equality, then ta-da, this is the optimal cost to go. Let's now produce an optimization problem that does that. Right, so we are going to search for a function, a negative function over every vertex. We're going to clamp the value of that function at the terminal point to 0. And then we're going to enforce this constraint right here, which is just the inequality version of the Bellman equation, right? So this constraint ensures that these functions are lower bounds on the true cost to go, right? So then if we push up on these lower bounds over the source set, then we're going to attain the true cost to go, right? Of course, that is if these functions have infinite flexibility, which in practice they never will, right? So we're going to need to come up with a finite dimensional approximation of this program. And we'll do so using semi-definite programming, right? So we'll instead search for polynomial functions over every vertex, and we will assert this constraint by using sums of squares programming, right? Where we'll be able to ensure that this inequality is valid over all corresponding points, right? And for details, again, we invite you to see the paper. Once we solve the semi-definite program, we get these cost-to-go lower bounds. Shown here is the heat map over the quadratic lower bounds. And then to extract the walk, we're going to use these lower bounds as guiding heuristics for incremental search. Now, many papers have been published on incremental search over graphs of convex sets, A-star, greedy, multi-step look-ahead. Here are some citations. For demonstration, here is just one-step look-ahead greedy search. That's what we use in the paper. And here at each step, we're trying to minimize the one-step look-ahead cost to go. That we saw in the Bellman equation, right? And this way we extract the walk just one step at a time. So now in the numerical experiment section of the paper, we wanted to take these robotic examples that we've been running with and compare the two transcriptions. The shortest walks, where we build the cost to go and then run incremental search, and the layered shortest path transcription, where we duplicate vertices. Indeed, we see that after an admittedly expensive initial cost to go synthesis step for the shortest walks, the solve time for incremental search of the shortest walks is up to an order of magnitude faster than seeking the shortest path through this layered graph. And moreover, the layered graph construction is so inefficient that for some of the more complex instances, it just fails to produce a solution outright. And for the instances where both algorithms do succeed, the solution costs are more or less comparable. To conclude, there are large classes of robotics and control problems that naturally involve some revisitation of operational modes, where the shortest walks in GCS formulation is much more natural and computationally efficient than the shortest path in GCS formulation. Finally, as for the dirty laundry, the cost-to-go synthesis step is, of course, the most expensive computational part, but it is justifiable in multi-query instances, right? So this is where we are running hundreds of instances over the same graph, where we can afford this one-time expensive step in order to then significantly speed up the subsequent queries. And finally, convex decomposition remains a bottleneck for our algorithm, as well as graphs of convex sets more generally, right? Collision-free space, skills, contact modes all need to be decomposed into these convex regions, and that's just a hard problem. And while automatic decompositions method do exist, they're still limited, and sometimes the number of these, the size of this decomposition really explodes. All right, thank you for your time, and I'm ready for some questions.